Hey everyone, welcome back to Tech Adventure. We will continue our journey into the field of embedded development skills. Today, we're diving into the fascinating world of communication protocols. Whether you're a seasoned developer or just starting out in the field, understanding communication protocols is essential for creating efficient and reliable embedded systems. In this video, we'll explore the ins and outs of embedded communication protocols from UART, I2C, and SPI to CAN and beyond. Get ready to unlock the secrets of seamless data transfer and real-time communication in embedded systems. Join us as we explore their crucial role in shaping the landscape of embedded systems. If you missed our previous video covering the essential skills required for embedded developers, I highly recommend checking it out first. Before delving into the specific protocol, first, understand what are communication protocols and why we need it in embedded development. A communication protocol is a set of rules and conventions that govern the exchange of data between two or more devices. It defines the format, timing, sequencing, and error-checking mechanisms for data transmission and reception. Communication protocols enable devices to communicate effectively, ensuring that data is transmitted accurately and reliably between sender and receiver. In embedded development, communication protocols are essential for several reasons. 1. Interoperability. Embedded systems often need to communicate with other devices or systems, such as sensors, actuators, displays, or other embedded devices. Communication protocols provide a standardized way for devices to exchange data, ensuring interoperability between different components and systems. 2. Efficiency. Communication protocols optimize data transmission by defining efficient data formats, encoding schemes, and error detection or correction mechanisms. This helps minimize bandwidth usage, reduce transmission delays, and conserve power, which are critical considerations in resource-constrained embedded systems. Three. Reliability. Embedded systems may operate in harsh or noisy environments where data transmission errors are common. Communication protocols include error detection and correction mechanisms to ensure the reliability of data transmission, even in challenging conditions. Four. Real-time communication. Many embedded applications require real-time or deterministic communication, where data must be transmitted and processed within strict timing constraints. Communication protocols designed for real-time systems, such as CAN, Controller Area Network, or Ethernet-based protocols with real-time extensions, facilitate timely and predictable data transmission. Overall, communication protocols are indispensable tools in embedded development, enabling devices to exchange data efficiently, reliably, and interoperably. By adhering to established protocols, embedded developers can design robust communication interfaces that meet the requirements of their applications and ensure seamless integration with other devices and systems. What are the different types of communication protocols? There are several types of communication protocols used in embedded systems, each with its own characteristics and applications. Here are some common types. These are just a few examples of communication protocols used in embedded systems. The choice of protocol depends on factors such as data rate, range, power consumption, reliability, and the specific requirements of the embedded application. In these protocols, some protocols operate synchronously, while others function asynchronously. To truly grasp these terminology and communication protocols, it's important to understand the key distinction between synchronous and asynchronous communication. Here are the differences. Please pause your video and go through it. Now, let's explore some of the common protocols utilized in embedded systems. We'll delve into UART, SPI, I2C, and CAN, gaining a comprehensive understanding of each one as we progress. UART, Universal Asynchronous Receiver or Transmitter. UART is a simple serial communication protocol commonly used for point-to-point communication between two devices. It operates asynchronously, meaning there is no clock signal shared between the transmitter and receiver. Instead, data is transmitted in a continuous stream with start and stop bits framing each byte. UART communication typically involves two signal lines, a transmit line, TX, and a receive line, RX. UART is widely used in embedded systems for tasks such as debugging, configuring peripherals, and communicating with external devices like GPS modules, Bluetooth modules, and RFID readers. It is relatively straightforward to implement and is suitable for low-speed communication over short distances. If you're enjoying the video, please consider giving it a thumbs up and subscribing to our channel. We value your input, so feel free to share your suggestions for topics you'd like to see covered in the comments section below. SPI, Serial Peripheral Interface. SPI is a synchronous serial communication protocol used for high-speed communication between a master device and one or more slave devices. It employs a master-slave architecture where the master device controls the communication bus and initiates data transfers with the slave devices. SPI utilizes four signal lines: a serial clock, SCK line, a master output slave input, MOSI line, a master input slave output, MISO line, and a chip select, CS or SS, line for each slave device. SPI supports full duplex communication, allowing simultaneous data transmission and reception between the master and slave devices. It is commonly used in embedded systems for interfacing with peripherals such as sensors, displays, memory chips, and analog-to-digital converters that require high-speed data transfer. I2C. I2C is a multi-master, serial communication protocol used for communication between multiple devices over a shared bus. It utilizes two bidirectional signal lines, a data line, SDA, for transmitting and receiving data, and a clock line, SCL, for synchronizing communication between devices. I2C supports multiple devices connected to the same bus, each identified by a unique address. It features built-in arbitration and collision detection mechanisms to ensure reliable communication between devices. I2C is commonly used in embedded systems for connecting sensors, EEPROMs, electrically erasable programmable read-only memory, LCD displays, and other peripherals that require moderate-speed communication and support for multiple devices on the same bus. CAN, Controller Area Network. CAN is a robust serial communication protocol designed for use in distributed real-time systems, particularly in automotive, industrial, and aerospace applications. It features differential signaling, where data is transmitted differentially over two wires, CAN high and CAN low, providing noise immunity and reliable communication in noisy environments. CAN supports a multi-master bus architecture, allowing multiple nodes to communicate on the same network. It features built-in error detection and fault confinement mechanisms, enabling reliable communication and error recovery. CAN is commonly used in embedded systems for applications requiring real-time communication, fault detection, and error handling, such as automotive control systems, industrial automation, and medical devices. Understanding the characteristics, advantages, and applications of each communication protocol is essential for embedded developers to choose the most suitable protocol for their specific requirements and design robust communication interfaces in their embedded systems. Deciding which communication protocol to use in an embedded system involves considering various factors and requirements specific to your application. Here's a step-by-step approach to help you make an informed decision. 1. Understand application requirements. Determine the data transfer rate required by your application. Consider whether your system needs high-speed or low-speed communication. Evaluate the distance over which data needs to be transmitted. Determine if communication will occur over short distances within a device or over longer distances between devices. Assess the power consumption constraints of your embedded system. Consider whether low-power communication protocols are necessary for battery-powered devices or if power consumption is less critical. 2. Consider environmental factors. Evaluate the operating environment of your embedded system. Consider factors such as temperature, humidity, vibration, and electromagnetic interference. Choose communication protocols that are robust and reliable in your system's environment. For example, CAN, Controller Area Network, is suitable for noisy industrial environments, while Bluetooth may be more suitable for wireless communication in consumer electronics. 3. Evaluate integration requirements. Determine if your embedded system needs to communicate with other devices or systems. Assess compatibility with existing hardware or communication infrastructure. Consider the availability of drivers, libraries, and development tools for integrating the chosen communication protocol into your embedded system. 4. Assess timing and latency requirements. Determine if your application requires real-time or deterministic communication. Evaluate the timing constraints and latency tolerance of your system. Choose communication protocols that can meet the timing requirements of your application. Real-time protocols like EtherCAT or CAN may be suitable for applications requiring precise timing control. 5. Consider scalability and flexibility. Assess the scalability of your communication solution. Determine if your system needs to support multiple devices, network topologies, or future expansions. Choose communication protocols that offer scalability and flexibility to accommodate future growth and changes in your embedded system. 6. Evaluate cost and complexity. Consider the cost and complexity of implementing and maintaining the chosen communication protocol. Assess factors such as hardware requirements, development time, licensing fees, and ongoing support costs. By carefully evaluating these factors and requirements, you can select the most suitable communication protocol for your embedded system. As we wrap up today's exploration into embedded communication protocols, we hope you've gained valuable insights into this critical aspect of technology. Remember, understanding these protocols opens doors to endless possibilities in building innovative embedded systems. If you found this video helpful, don't forget to like, share, and subscribe for more insightful content. Stay tuned for our next adventure in the world of embedded technology. Until then, happy learning